Bougie,
No.
Paige wants you to know this doesn't count towards your bell ringer days. Alright, now we're live. Alright, so today we're talking about exponential growth and decay, whether it's on graphs, we're going to talk about tables, all sorts of stuff, all sorts of fun things. So we talked about doing exponential growth and decay problems where we plug things in, found values for future scenarios. Now we're just going to talk about an exponential growth function. So the format for an exponential growth function is y equals a times b to the x power. Y equals a times b to the x power. Exponential growth happens when our b value in that function is greater than 1. So b has to be greater than 1. If we're trying to look at a graph, we're trying to determine is it going to be an exponential growth function, exponential decay function. It's pretty easy to tell. Exponential growth functions will always be this form. They'll always start really small on the left and exponentially get bigger as they go to the right. So growth, it's growing as it goes to the right. Pretty easy to remember, right? Okay. So let's talk about how the graph is affected when a or b value changes. Take out your calculators once. Take out your calculators. Put these three into your calculator. Y equals 2 to the x, y equals 5 in parentheses to the x, y equals 4 times 3 in parentheses to the x. We had a couple things to answer on there. So I'll do it as well. Y equals, I already got an NIT. Okay. So if you graph those, make sure you remember which one is which. Some of us can't tell because they're all the same color. It's fine. We'll talk about them.
Yeah, all mine the same color. I have the old.
It's alright.
What's the third value you put in?
Y equals 4 times 3 in parentheses to the x power. Okay. I'm going to make my window smaller. I want to see it better. So I'm going to go like -15. Let's try that. Go by ones.
I really don't like that even.
Oh, that looks better. Look at that.
What did you change your window?
My window, I put as x minimum of -15, x max of +15, and I went my x scale of 1. And then my y window, I think I went -50 to +50, my guess. So I can't really see the top of my graphs very well, but I can kind of see how they space out a little bit. First question, are they all exponential growth?
Yes.
Yes. How do you know that? How do you know that looking at the graph?
To go up.
They go up as they go to the right, correct? How would you know that if you just looked at them? Let's look at them again. Y equals, remember it's supposed to be y equals a times b to the x, right? What is the stipulation for that? What does it say? B has to be
Greater than 1.
greater than 1. So, 2, 5, 3. Is b greater than 1?
Yes.
Yeah, in all of them. So I know they're all going to be exponential growth. I know that because b is greater than 1, or we looked at the graphs. Now, what do the numbers in front of that do to the graphs? If I look at these, my graph changed. I had y equals 2 to the x. That's my base one over here. Then it happened to be y equals 5 to the x. That red one, if I back out a little bit more, I want to do my window. I'm going to change it to... Now it's going to take a second to graph again. But I just want to see what happens to them. Look what happens. Why are these ones different than the blue ones? What happens when I change my number up front?
Because when they go up, they're closer to the y-axis.
They're closer to the y-axis, so they get steeper, right? Well, let's look at it. As my numbers got bigger, my graphs got steeper and steeper. So as that A value in front changes, as that A value gets bigger, the graph is going to get steeper. So as the A gets bigger, it's going to get steeper. Right? Now, let's go back here again. Let's zoom in on that x-axis once. So let's go like y value of -10 to 10. That's still not good enough. That's going to be watching graph. Come on. Fine. So let's get even closer yet. Let's go. Let's make 3. Let's go -2 and 2. So now let's graph it. I want to get really close to that y-axis. Come on. Still not really great, but that's alright, that's fine. What do you notice with that x-axis? With all these graphs, all 3 of them? What do you notice? Tobias?
They all start to go up at different points.
They all start to go up at different points, but specifically, what do you notice about the graphs and the x-axis?
Pretty much 0.
It's pretty much 0. Does it ever go below the x-axis? No. And it'll actually never reach the x-axis. These look like they get really, really close, but it'll never reach that x-axis because we have what we call a horizontal asymptote. We're not going to get too in-depth with asymptotes. What they do though, so if I drew it on here, it'd be on the x-axis. Those graphs, those functions will never cross that line. The asymptote separates where it's going to cross and where it won't. So we have a horizontal asymptote on our x-axis. Our graph will never touch it, will never cross it. It'll get really, 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 really close to it, but it'll never actually get there. It'll never get to 0. It'll never cross 0. Just a nice little fun fact. Alright, that's it with exponential growth functions. It'll never go negative like that. Alright? We have a horizontal asymptote. Now, like I said, we're not going to get too deep into asymptotes. We'll talk more about those in pre-calc and calculus. Alright, any questions about exponential growth right now? Nothing? Beautiful. Now let's talk a little about exponential decay. So exponential decay, a format for an exponential decay function is also y equals a times b to the x. Same as it was for exponential growth. Y equals a times b to the x. Now, the difference is exponential decay happens when b is between 0 and 1. When b is between 0 and 1. Also notice, exponential decay graphs look a little different than exponential growth, don't they? What's the difference? Q.
It slopes down.
It slopes down, right? It starts growing, it starts way up top here and slopes down and goes over. So it's going down from left to right. Growth's going to go up from left to right. Decay goes down from left to right. It's a pretty easy way to distinguish it on a graph. So what happens now if we change the value of a or b for these ones? Put those ones in your calculator. I'll do the same. So let's go y equals. Let's go, what were they? 1/2 x 1/4 x and then we had 6 times 1/5. Okay, we all got those 3? So I'm going to change my window again just to make sure you can see them. Let's just go 15. Alright. So now if I graph them. Can we tell their decay pretty easily?
Yeah.
Yeah, right, they're coming down at a deep, steep angle, flattening out. Could you tell their decay before you put them in your calculator?
Yeah.
Yeah.
Let's look at them. How so?
The numbers are in between.
They're all fractions.
They're all fractions. They're all between 0 and 1. Now be careful. We might give you one that's a fraction bigger than 1. Would that be decay or growth? That'd be growth. These ones are all 1/2, 1/4, 1/5. Those are all below or between 0 and 1, so I know it's going to be decay. So what number makes them decay? Right? 1/2, 1/4, 1/5 will make them decay. Alright, so let's look at what they do to the graph. So the blue one is 1/2 to the x. The red one is 1/4 to the x. The magenta one is 6 times 1/5 to the x. What's happening? My numbers are changing. 1/2, then 1/4, then 1/5. Are they getting smaller or bigger? Those numbers are getting smaller, right? 1/2, 1/4, 1/5. What's happening to their graphs? They're getting closer to the y-axis, right? They're shifting over. Some of them, even the one that has 6 times, even gets a little steeper. It doesn't go up quite as slowly, even though they all go up pretty quickly, as the others. So as A and B change, things are going to get steeper and less steep. Alright? Does that make sense? Right, so as we change our values, things get more steep, less steep, things like that. Now, why don't they cross the x-axis again? An asymptote, right? There's a horizontal asymptote there as well. They'll get really, really close to that x-axis, but it'll never cross it. That asymptote will say, you cannot cross here. It has to keep going. It'll get really, really close, but it'll never actually get there. Alright? Does that make sense? Do you understand what an asymptote is now?
Sort of.
Sort of. Right? It's a line that a function can't cross.
Oh.
So we would have a horizontal asymptote at the x-axis. It can't cross that line. That's about as in-depth as we're going to get with asymptotes for right now. We're not going to go about drawing them, all sorts of stuff like that. Yes, Mason?
So, what do the numbers do in front of the, sort of like D? Like, do they make it go steeper?
So yeah, so it makes it go steeper, right? So if our A value is bigger, as A gets bigger, like that 6 is way bigger than the 1s out here, it gets steeper, makes it go up, right? Makes it go up faster, okay? Makes it go down faster. Pretty cool. Any questions? Like I said, this is the first time we're kind of doing it this way, so just bear with me. Alright? Alright. Then let's keep moving on. For each equation, we'll identify it as exponential growth or decay. Well, first one, y equals 3.34 times 1.67 to the x. Growth or decay? Growth. How do you know that?
The number's larger than 1.
1.67. Our b value is greater than 1. Good. Alright, what about the second one? Y equals 0.8 times 0.54 to the x power. Decay. 0.54 is between 0 and 1. What about c? Y equals 4.5 times 4 to the negative x power. Ooh, we have some say growth, some say decay. Who thinks growth? Who thinks decay? Who doesn't want to put their hand up? Alright, who said growth? Who did you say growth? What? Why?
Because b is greater than 1.
Okay, why do you say decay?
Because when there's a negative exponent, it's almost always like a decimal.
It's almost always a decimal, right? Was our original exponential function a times b to the negative x or positive x? Positive, so we need to make that a positive x. So it would be y equals 4.5 times 1/4 to the positive x. Because remember, we flip it to make it a positive exponent. Flip it. So is it going to be growth or decay? Decay. Right? 1/4 is between 0 and 1, so it's decay. Good. So gotta be careful. It's tricky sometimes. Alright? Alright, next one. Y equals 2 times 8/5 to the x. Growth. Because 8/5 is bigger than 1. It's 1.6. So B is greater than 1. Good. So we all know how to see it from a function. We just look at the function if it's growth or decay, correct? Yeah? Okay. For each graph below, identify the graph as exponential growth or decay and estimate its initial value. We haven't talked about initial value yet, so let's go and name them either growth or decay to start. The first one, what do you look like? Growth, right? It's going up from left to right. So first one we'll say is growth. Okay? Second one, we'll use the black marker. Growth. Left to right, it's going up. Growth. And then the last one down here in the bottom. Decay. That's ugly. Decay. Good. So it's going down from left to right. Now it also asks you to list the initial value. What do you think its initial value? What does that mean? What do you think? What? What do you think, Colton?
I said where it crosses the y-axis.
Where it crosses the y-axis. That's perfect. It's exactly where it is. Where x equals 0. Right? We just want to figure out, kind of estimate where does it cross the y-axis. That's its initial value. So the first one, initial value is approximately 2.5. We can all agree on that? Right? It's an estimate. We're looking at the table, or we're looking at the graph. Okay? The second one. Well, a little tougher. 7. Well, we can agree on 7. That's fine. Right? It looks like it crosses right about 7. Maybe a little bigger than 7, but it's an estimate. So it's approximately 7. And then C.
8.
Ooh. I think it's a little bit below 8.
No.
You don't think so?
I think it's an estimate, so it's fine.
You think it's an estimate, so it's fine. That's alright. It's an estimate, right? So initial value we'll say is approximately 8 then. If you guys want to use nice numbers. Alright? Obviously, try and get it as close as possible. You think, if you're off by a few, if we ask you for initial value, we ask you to estimate it, obviously there's some leeway there. It's not going to be perfect. Alright? Any questions? Keep chugging. Alright, now we're going to talk about tables. Exponential growth and exponential decay in a table. We want you to tell what kind of function is it going to be just by looking at the table. How do you think we can do that? Fuji?
As the x value would increase, the y value would increase on a growth, and it would decrease on a decay.
Perfect. So as the x value goes up, as I go from left to right, if it's going to be growth, that y value should go up too, so we know it's climbing. If the y value goes down, boom, we know it's going down like decay. This way. Decay's like that. So, the first one, as x gets bigger. So as x is getting bigger, what happens to y?
Smaller.
It's getting smaller, it's going down, so that means it's going to be decay. Does that make sense to everybody? So as I'm going on a graph, as I'm going from left to right, as my x values are getting bigger, if my y values are going down, that means my graph's going to look like that. If my y values only go left to right, my x gets bigger, go up, then it's going to go up like it's growth. Does that make sense? Okay, so the second one. As my x values get bigger, they get bigger. What happens to y?
Also gets bigger.
It also gets bigger, so it's a growth. Wonderful. So lastly, my x values are getting bigger. What's happening to y?
It's bigger.
Gets bigger as well, so it's growth. Look at all the stuff we're learning today. How much fun. You guys look like you're having a ton of fun. tired. Oh my goodness. It is Friday. What time are we done here?
I see.
25. Oh, alright, perfect. So we're going to talk a little bit also log functions and corresponding exponential inverses. It's on your paper. We're going to take a second here to talk about they are actually inverses. We talked about that, right? We talked about how a log is the inverse of an exponential. We talked about this? You agree?
Yeah.
When we first started logs, we said that. Here are the graphs. You'll notice an exponential function, a log function. They're an exact mirror of each other if we folded them over, right? That's what it means to be an inverse on a graph. Now, same thing over here. Exponential, exponential, exponential. Log functions would be the inverse. Now, we might ask you to figure out on your calculator which one is which on the homework, like match them up. All you do is punch them into y equals. So if I ask you which of these graphs is log base 2 of x, put it into your y equals and look on your graph. And we're going to ask you to match them up. You need to be able to tell which is an exponential function, which is a log function. Right? And all you do is plug them into your graph on your calculator and match them. Okay? You should know a log function is the opposite or the inverse of exponential, because we all know what an exponential function looks like now. We just learned it today. Right? So, how do the graphs of the log functions corresponding exponential inverse compare? We just talked about that. They're mirrors of each other. Right? We just said they are inverses, so that we could flip them over, fold it over, they'd be exactly equal. They are inverses. They mirror each other. Now, talking about asymptotes again. Do you see any on these graphs? Do you see any on these graphs? Grace?
It's y equals x.
Y equals x. That's one asymptote.
That's
Awesome. There's two more.
what?
Now, they're for different graphs, but there are two more. Liam, let's look at the exponential. Is there an asymptote for that graph?
Yeah.
Yes.
What is it?
X.
The x-axis. There's a horizontal asymptote on the x-axis for our exponential graph. Same thing over here. What about our log functions? Is there an asymptote for the log functions that you could maybe see? The y-axis, right? It's a vertical asymptote. So it's an inverse, right? X and y. So the log functions have one on the y-axis. It's a vertical asymptote on the y-axis. Does that make sense? Like I said, we're not going to do a ton with asymptotes. We're just looking at the graphs. Any questions?
Nope.
Okay. I think we have one application problem to practice. Let's do it together. I think that they want to do it. Let's do it together. 1999, wind turbines in Europe generate about 5 gigawatt hours of energy. Over the next 15 years, the amount of energy increased about 59% per year. Write a model giving the amount E in gigawatt hours of energy T years after 1999. So what type of problem is this? Exponential growth, exponential decay, compound interest. Exponential growth, right? It's growing. So y equals a times 1 plus r to the t power. Or in this case, we want it in the amount E. So y is going to be E equal to, what's my initial amount? 5, right? I'm starting at 5 gigawatt hours. 1 plus, what's my rate? 59%. So 0.59. And what's my time?
10. Yeah.
T right now. In part A, it's T. I just want to know in T years. Okay? That's all I asked for. That's my model. Right? I'm just plugging in what I know so far. So energy is going to equal 5 times 1 plus 0.59 to the T power. Great. Second part asks me, how much wind energy was generated in 2009? Well, I started in what year? 1999. I'm going to 2009. 10 years, so T equals 10. Just plug it in. E equals 5 times 1.59 to the 10th power. So E should be approximately let's say to the 10th place. Let's say 10th place. Beth, what'd you get?
516.3.
516.3. Now, what's our label going to be for this? Gigawatt hours, right? We're talking in terms of energy. We're talking in terms of gigawatt hours up here. So, I don't know if that's the actual abbreviation for gigawatt. I highly doubt it. But I'm just writing because I ran out of room. Okay? Then how would I do the last one? Let's just set it up. I'm not going to ask you to write it down because we only got about 5 minutes left. Let's just set it up and then you can figure out if you want how to solve it. I want to know estimate what year of 80 gigawatt hours of energy. Tobias, how would I set it up?
So, 80 would replace 80, so you have 80 equals 5, and then 1.59, and there's the power of x.
The power of x or power of t or whatever you want, right? Either variable. So then you guys all know how to solve something like that now, right?
Yeah.
Isolate this, divide by 5, switch it to log form, and you're good to go. Do we need to go through it?
No.
Alright, if you want to do it, check your answer. Notes are on Schoology.